PSEM is a unique capability of PC signal for signal enhancement and identification. Dynamic load variation on a rotating shaft tends to momentarily speed up or slow down the shaft rotational speed, which causes the RPM, or the sync frequency component, to be a quasi-periodic signal rather than periodic. When the RPM reduces or increases even only slightly, the instantaneous frequencies of all other RPM-related signal components, such as sync harmonic, bearing signal, etc., will also respond in kind. As a result, this produces a unique phase correlation with the RPM. PSEM utilizes a phase-time conversion algorithm to resample the raw data by synchronizing its sampling intervals with the instantaneous phase of a user-specified reference signal component. At the PSEM reference frequency or FR. For rotating machine application, the PSEM reference signal is typically a known RPM-related signal, such as blade passage, gear mesh, etc., which often has strong signal-to-noise ratio, preferably greater than 20 dB. After PSEM resampling, the original quasi-periodic reference signal at FR will be transformed into a periodic signal. More significantly, all other RPM-related signal components that are directly phase correlated with PSEM reference signal will also become periodic. As a result, they become enhanced and more detectable in new PSEM PSD. The PSEM phase synchronization process is similar to the traditional order tracking method, except, PSEM does not require a pulse type of speed measurement, or speed probe, for its signal processing. This chart shows the PSEM algorithm. The input includes two measurement channels, XR, T, and XT. XR, T, is the PSEM reference channel that the instantaneous phase of PSEM reference signal is computed from. It is a raw signal with uniform sampling time intervals. XT is the analysis channel that the PSEM enhancement is applied to. It is also a raw signal with uniform sampling time intervals. In most cases, XR, T, is the same as XT. If XT already contains a sufficiently strong PSEM reference signal. Otherwise, select another measurement which contains the strongest reference signal as XR, T. The analysis time frame should be within a stationary time period where the PSEM referenced frequency remains relatively constant. In the PSEM menu, two key parameters are to be specified. The PSEM reference frequency FR and the passband of bandpass filter. The first step is to perform complex demodulation at FR, in order to generate its instantaneous phase phi, T. This demodulation also requires phase unwrapping with a resampling time constraint applied. Subsequently, a phase time conversion is performed to convert the instantaneous phase phi, T, into a realignment time signal delta, T. This completes the processing of the reference channel. The realignment time signal delta, T, is then applied to the analysis channel XT, in order to realign the original uniform sampling time into uniform phase intervals at FR. The output of this intermediate new signal Y, T, will have uniform phase intervals at FR. However, its sampling time intervals will become non-uniform after realignment. Since a signal with non-uniform sampling time interval is not a convenient format for analysis, an additional step is performed to resample Y, T, back to uniform time interval to generate the final output PSEM signal Z, T. The net effect of this process is that the original quasi-periodic signal at the PSEM reference frequency in XT, will be transformed into a periodic signal in Z, T. More significantly, All other signal components in xt, which is phase correlated to the PSEM reference signal, will also automatically become periodic. As a result, signal enhancement can be achieved on all the other phase correlated signal components.